In the sterile confines of a shielded facility, the birth of the Champ missile begins with the assembly of its most critical component, the pulse core. A robotic micro-alignment armature, guided by laser interferometry, initiates the assembly process with micron-level precision. Every movement is verified by a laser interferometry system, ensuring the base is perfectly centered within its lead-lined housing. These magnets are positioned with extreme care to maintain the stability of the core's flux during high-power discharge. High-purity copper coils are wound around the housing to focus the electromagnetic pulse. Precision laser welding secures the induction coils, ensuring a zero-resistance path for the upcoming energy surge. To prevent premature radiation leakage, the assembly is capped with a dense lead-lined shielding lid. The lid is pressurized into place, initiating the first stage of the hermetic sealing process. Microbolts are torqued to exact specifications to maintain internal pressure during the pulse's intense thermal expansion. Internal atmosphere is evacuated, creating the high vacuum environment necessary for the microwave resonators to function. With the core hermetically sealed and aligned, the heart of the Champ missile is ready for integration into the energy storage system. We begin with the empty reinforced composite midsection, the primary structural vessel for the weapon's power source. 20. A high-voltage dielectric spacer is meticulously positioned to provide electrical insulation against the inner airframe. The first cell is seated into the mounting guide, initiating the buildup of the multi-megawatt energy bank. An iridescent dielectric coating is applied to the terminals to prevent premature discharge and arcing. Secondary locking clamps are engaged, securing the first tier of the energy storage payload against flight vibrations. Heavy-gauge silver-plated bus bars are introduced to facilitate the rapid flow of current. Laser welding creates a permanent high-conductivity bond at the primary terminal junctions. Vertical interconnects bridge the tiers, creating a unified high-voltage energy reservoir. The external bracing is finalized, locking the immense electrical power within the missile's core. The integration is complete. A multi-megawatt bank of capacitors is now fully secured and ready for discharge. The assembly moves to the forward bulkhead, where the precision-engineered gold-plated waveguides are first aligned. Automated torque systems secure the manifold to withstand the intense thermal stresses of HPM bursts. The conical HPM antenna base is moved into position, featuring the critical phase shifter servos. Internal servos are fine-tuned, calibrating the phase shifters for surgical energy direction. A low-power pulse test verifies the electromagnetic seal and the beam's directional accuracy. Thermal shielding is wrapped around the assembly to protect sensitive electronics from heat generated during emission. UV curing instantly hardens the seal, ensuring structural integrity during high subsonic flight. A high-efficiency turbojet engine is lowered into position, designed for the extended loitering times required for multiple HPM engagements. Every millimeter is measured. The engine must sit perfectly centered to maintain the missile's aerodynamic profile. The engine is locked into the mating cradle, anchoring the motive power of the Champ to its structural spine. With the engine secured, the missile's center of mass is finalized, allowing for the installation of the control logic. Next, the fuel delivery system is connected, linking the internal reservoirs to the high-pressure injectors. Above this engine, we install the missile's brain, an advanced GPS-denied autonomous navigation module. This system allows the Champ to navigate via terrain mapping and inertial guidance, making it immune to electronic jamming. Sech-Desmit Piektais. High-bandwidth fiber optics connect the navigation unit to the turbine's control computers. Precision soldering secures the logic links, creating a permanent vibration-resistant connection for the flight software. The propulsion system comes to life, confirming that the engine and its intelligence are perfectly synchronized. With propulsion and intelligence integrated, the missile is now a fully autonomous platform ready for its mission payload. A microscopic layer of conductive primer is applied, creating the necessary base for the radar-absorbent material to bond. Critical leading edges receive a graded application to further reduce the radar cross-section from forward-facing threats. Infrared curing banks are deployed rapidly, hardening the RAM coating into a durable aerodynamic shell. A final laser metrology scan verifies the coating thickness is accurate to within 10 microns across the entire airframe. Heavy-duty locking collars engage, creating a unified, rigid aerodynamic structure capable of high subsonic flight. Hydraulic systems engage, initiating the sequence to transition the missile from its dormant state to active deployment. The rotary launcher begins its slow, precise revolution, bringing the selected Champ missile into the drop position. The internal launcher indexes the payload with surgical precision, aligning the missile with the bay's release axis. The aircraft's umbilical connection is severed, transferring full command and control to the missile's internal flight computer. Internal battery systems take over, powering the sophisticated microwave emitters and navigation arrays. The bomb bay doors cycle open, exposing the Champ to the harsh high-velocity environment of 30,000 feet. The payload is now vulnerable to the slipstream, ready for gravity-fed separation into the combat zone. Gravity takes hold as the Champ missile begins its descent, falling away from the safety of the mothership. As it reaches its designated drop speed, the airframe undergoes intense aerodynamic pressure. Tail fins lock into position, providing the necessary control surfaces for autonomous navigation. The turbojet intake opens, gulping in the thin, cold air required to ignite the missile's propulsion system. The compact turbojet engine spools up its turbine blades, reaching operational RPMs within seconds. With the engine at full power and flight surfaces locked, the Champ missile begins its stealthy, low-altitude approach to the target zone. The emitter sends out rapid electromagnetic pulses, searching for the first touch of the terrain below. The flight control system initiates a steep descent, moving the Champ missile out of the vulnerable high-altitude detection zone. Descending through the cloud deck, the radar altimeter begins to map the jagged contours of the landscape below. Flying just above the tree line, the missile's signature is masked by the complex clutter of the natural environment. The total radar horizon occlusion is achieved. The enemy's long-range detection systems are now entirely bypassed. With the silent infiltration complete, the Champ missile's is now perfectly positioned for its final approach to the primary target. The Champ missile approaches its primary objective, a hardened underground command bunker, moving with predatory stealth. The antenna focuses the beam, narrowing the microwave energy into a surgical cone of electronic disruption. The first pulses released an invisible wave of high-power microwaves cascading toward the bunker. Communication with the outside world is severed instantly as the facility's transceivers are fried. Telemetry confirms the thermal signature of a successful electronic neutralization within the target zone. The missile sheds the excess thermal load from the burst, preparing its power systems for the next objective. The strike is complete. No kinetic damage was dealt to the walls, yet the facility is effectively destroyed. The first strike has proven the era of electronic warfare has reached a new non-kinetic peak of lethality. The multi-target trajectory algorithm initiates a sharp bank, realigning the missile toward the coastal defense perimeter. Advanced sensors lock onto the high-gain radar arrays, identifying the critical nodes of the enemy's early warning system. The HPM antenna directs a concentrated burst of microwave energy directly into the radar's feed horn. The energy surge overloads the sensitive receiver electronics, melting the internal circuitry in milliseconds. Control systems fail as the guidance processors are fried, rendering the surface-to-air battery completely inert. Gaining altitude for a broader sweep, the missile prepares to address the regional power distribution nodes. The multi-target trajectory algorithm identifies the critical substations feeding the city's communication grid. A wide aperture burst is released, targeting the high-tension transformers and switching stations. Commercial districts go dark as the energy pulses ripple through the urban infrastructure, bypassing physical barriers. Communication networks and digital displays are silenced, leaving the enemy in a state of total information isolation. Telemetry confirms the total non-kinetic neutralization of the targeted electronic warfare and power assets. With its mission parameters fully satisfied and its electromagnetic energy stores completely depleted, the Champ missile initiates its terminal phase. The titanium actuators adjust the tail fins to a steep angle of attack, preparing the airframe for a rapid descent. Guided by GPS, denied inertial navigation, the missile identifies its terminal impact point within the deep-sea trench. The nose pitches down, entering a ballistic trajectory designed to ensure no kinetic impact on civilian infrastructure. Onboard memory modules undergo a multi-pass secure erase protocol, purging all mission data and encryption keys. Upon impact, the Champ missile enters the water with surgical precision, minimizing surface debris. Sinking beyond the reach of recovery, the hardware is interred in the lightless depths of the ocean. At the bottom of the trench, the Champ system comes to its final rest, its operational life cycle complete.